Welcome back. In this section, we're going to be looking at graphing the sine function and the cosine function, and also looking at transformations of the sine and cosine function. So as far as the basic shape, y equals sine of x, we can come up with the graph of that without too much difficulty if we're using the unit circle definition of our trig functions. Remember that for the unit circle, sine is just the y value as we travel around the unit circle. So as we make our way from 0 radians to pi over 2 to pi to 3 pi over 2 and back to 2 pi, our y values on that unit circle are going to be the values of sine of x. So at 0 radians, the y value is 0, so sine of 0 is 0. At pi over 2, the y value is 1. At pi, the y value is 0. At 3 pi over 2, our y value is negative 1. And at 2 pi, our y value is back to being 0. So our graph is going to oscillate. It's going to increase up to 1, then decrease down to negative 1, and then come back up to 0 again. And of course, because sine is a periodic function, it repeats itself, we're just going to do that same shape over and over again. So if we wanted to take a little look, we've got some properties that we can now say about our sine function. So the first one is the domain, which should not be a big surprise for us. If we're thinking again about sine of x being the y value on my unit circle, no matter what angle you're talking about, there is always a y value on that unit circle, so any angle can be the input for sine of x. For the range, the biggest y value that we have on the unit circle is 1, and the smallest one we have is negative 1. So those are the largest and smallest values for sine of x. So sine of x's range is from negative 1 to 1. We also have an x-intercept at 0, 0, and a y-intercept is also 0, 0. We've also got some other x-intercepts at all of these whole number multiples of pi, positive and negative pi, positive and negative 2 pi, 3 pi, and so on. And we see some of them coming directly from this, the 0, the pi, the 2 pi being x-intercepts. The rest of them also come from periodicity, that we'll also have an x-intercept at 3 pi, then at 4 pi, then at 5 pi, and also at negative pi, negative 2 pi, negative 3 pi, and so on. We already knew from 7.4 that sine was an odd function. We already knew that it had a period of 2 pi, so none of that was a surprise. And now we can also add to the things that we know about sine of x that it has this graph. So here I've drawn two full cycles of the sine function. This is the one full cycle that came from the unit circle, going around from 0 radians to 2 pi. And then the second cycle, I just sort of copied and pasted the first one, because of course the graph is identical for each cycle. It just repeats itself again and again. So that means if we're taking a look at the sine function, anytime I graph one cycle, there's going to be 5 points in total that define that sine function. These 3 points that are the x-intercepts, and then I have the maximum value and the minimum value. And that's going to be the same thing for cosine. The graph of cosine, each cycle will also be made out of 5 key points. And speaking of cosine, let's have a look at it. Same sort of a thing here. If we're thinking about the unit circle definition, that's an easy way to come up with our values for cosine. On the unit circle, cosine is just the x value. So if we're traveling around the unit circle from 0 radians all the way to 2 pi radians, we just have to keep track of what was the x value. And so at 0 radians, the x value is 1. Then our x value is now 0. Then as we travel to pi radians, the x value is negative 1. Then as we travel to 3 pi over 2, the x value is back to 0 again. And then at 2 pi, our x value is back to being 1. So the cosine graph is going to be doing a similar thing to the sine graph, oscillating, going from 1 to negative 1 to back to 1, and then repeating it, going up and down forever. And we have similar sorts of properties that we could say here that we said about sine. So for same sorts of reasons, the domain is all real numbers and the range is from negative 1 to 1. We always have an x value on the unit circle, so for any angle there will be a value for cosine. And for the unit circle, the biggest and smallest x values are -1 and 1. So the biggest and smallest values of cosine are from -1 to 1. And then, of course, we've also got x-intercepts at all of these half pi's, half pi, 3 pi over 2, 5 pi over 2, 7 pi over 2. All of these odd pi over 2's will have x-intercepts. And then from 7.4, again, we knew that the symmetry was even symmetry and the period was 2 pi. So our graph of the cosine function looks kind of like this. And one thing I hope you'll notice is that basically the graph of the sine function and the graph of the cosine function are almost identical. The only difference is that one is looking a little shifted compared to the other. Remember that our cosine function starts at 1, goes down to -1, and then comes back up to 1. Sine started at 0, went to 1, to -1, and then back to 0 again. So kind of if we're looking at this graph of cosine, you could imagine it as a shifted sine graph. It's like a sine graph that's been shifted to the left by pi over 2. This also means that when we're looking at the graph of a trig function, if it's oscillating like this, if it's going up or down and up and down and up and down, it could be a cosine graph, or you could describe it as being a sine graph. So this particular graph here, I'm saying it's y equals cosine of x, but I could also say that it's a shifted graph of the sine function. It's been shifted to the left by pi over 2. And you'll be able to come up with all sorts of other ways to describe this exact same graph. That's one of the nice things about trig functions, but it's also one of the challenging things about them, is that if I just give you a graph, there's not only one correct answer for what is the equation that gives that function. So let's talk about some transformations of our trig functions, sine and cosine. We're going to do the transformations kind of in two phases here. First, we're going to talk about the stretches that we have that we could apply to them, vertical stretches and horizontal stretches. And then later on, we'll look at the shifts, the vertical and horizontal shifts. So right now, when I write a sine bx or a cosine bx, I've got a vertical stretch going on, possibly a vertical flip as well. I've got a horizontal stretch going on, possibly a horizontal flip as well. And it's basically the same sort of ideas that we were talking about back in section 3.5. So if this number was just a positive number, then it's a vertical stretch. If a was a negative number, it would be a vertical stretch and also a flip. If b is a positive number, then it's just a horizontal stretch. If b is a negative number, it's a horizontal stretch and also a flip. There's a little bit of new terminology to introduce here. So we already have talked about the period of our trig functions, sine and cosine, both being 2 pi. And remember that for the horizontal stretch that's in front, the value b, what we'll be doing is taking each x value that we have and dividing it by b. So that means if you're thinking about what is the period for this function, we could say, well, normally it would be 2 pi, but we're dividing everything by b, so really our period is 2 pi divided by b. I have to be a little bit cautious here, and I said 2 pi divided by b, but really I should be saying 2 pi divided by absolute value of b. And the reason for this is because the period is a length. It's how far it is from the beginning to the end of one cycle. And of course, lengths need to be positive, or distances need to be positive. So if your b was a positive number already, then good for you, 2 pi divided by b, that would be your period. If b was not negative, b was not positive, we would have to make it positive. So 2 pi divided by absolute value of b. That's how we'll talk about the period of our sine and cosine function. As far as the value in front, the a, the vertical stretch, we can talk about that as well. So normally if we're looking at our sine or our cosine graph, and I'm just going to go back to it just so we can have a little look at it. Cosine graph and the sine graph are the same in the sense that they have a distance of 1 unit from the middle to the top or the middle to the bottom. We would call for this cosine function, I would say that it has an amplitude of 1. Amplitude is exactly that distance. Amplitude is the distance from the middle to the top, or you could think of it as the distance from the middle to the bottom. Either way, that distance is 1 unit. If I stretch my graph vertically, that's going to change that distance. So if you had a number a in front and you multiplied all of your y values by a, then instead of having a maximum value of 1 and a minimum value of -1, you'd have a maximum value of a, whatever that is, and a minimum value of -a, whatever that is. And that means for your amplitude is the distance from the mid to the absolute maximum value. And so in that case, we could say that our amplitude, that distance, should be absolute value of a. Again, kind of like the same thing as with period, I'm putting an absolute value on because amplitude, just like period, it is a distance. It's the distance from the middle to the top or the distance from the middle to the bottom, if you wanted to think of it that way. Either way, distance needs to be a positive number. So if a were negative, if I were talking about amplitude, then I should put an absolute value on it when I say there's my amplitude. It's absolute value of a. So for these two functions, finding the period and amplitude is not too bad because all we need to do is do a couple of little quick calculations. For the first one, where I've got -3 sine of x over 7, it might be maybe easier for you if I first rewrite this x over 7 as 1/7 times x. So that means when I'm thinking about talking about the period for this function, that would be 2 pi divided by absolute value of 1/7, or 2 pi divided by 1/7, which is the same thing as 2 pi times 7 over 1. So in other words, the period for this function is 14 pi. It takes 14 pi units to do one full cycle, so it is stretched out by a factor of 7. It's 7 times wider than the original sine graph was. If we're thinking about the amplitude, the number in front of our function we have is -3, so for my amplitude for this function, that would just be the absolute value of -3, which is just 3. So in other words, from the middle to the top or the middle to the bottom of this graph, it would have a distance of 3 units. Okay, let's do the next one. We've got 1/2 cosine of -4x, and so same sort of thing that I did before, I'll do here. I'll say that if we're talking about the period, that it would be 2 pi divided by the number in front of the x, absoluted. So in other words, 2 pi divided by absolute value of -4, which is 2 pi over 4, which simplifies to be pi over 2. So this is a graph that's been compressed by a factor of 4. It's 4 times narrower than the original cosine graph. So the original cosine graph would take a full 2 pi to do one full cycle. This graph does a full cycle in pi over 2 units. So it's 4 times as narrow as the original graph. As far as the amplitude goes, then same thing as before. That is the absolute value of the number that's in front of our trig function. So the amplitude here is absolute value of 1/2, which is just, of course, 1/2. So it's 1/2 as tall as the original cosine function. It has a distance from the middle to the top or the middle to the bottom of 1/2. So now if we're coming up with an equation of this function, like I said, there were a couple of ways we could think about this, because any sort of oscillating function like this you could describe as a cosine function or a sine function. You might have to involve a shift if you were doing that. I'm going to take the easy way out, and I'm going to match this with a basic shape, and I won't have to start thinking about shifts as well. I'll just say that if we were comparing this graph to one of the two trig graphs that we've looked at before, so if we compare it to the sine graph, The sine graph started at 0, then started oscillating, going up and then down. The cosine graph started at 1 and then did its little oscillating, going down and then up. And so the graph that I've got here looks more like a cosine graph than it does a sine graph. So if I'm looking at this one, I would say, okay, this is some sort of a cosine graph, and I'll imagine it as a cosine graph that's been stretched. So instead of starting at 1 and then going down to -1 and back up to 1, it's starting at 3, then going down to -3, then going back up to 3. So I would say that this is 3 times a cosine function, because I've taken my original cosine function and all the y values we can see have been multiplied by 3. If we're thinking about the period for this one, normally the period would be 2 pi. Here the period is pi. We have our period that's half as big as the original one. So in other words, our period is 2 pi divided by whatever absolute mystery number that I'm looking for. So this is my mystery b that I'm searching for, and I know that 2 pi over absolute value of b would be my period, and in this case the period is pi. So solving for that, I can say, well, absolute value of b should be 2 pi over pi. Or in other words, b should be, absolute value of that should be 2. So now, when I'm thinking about this, this actually is going to point to more than one answer for this question. Originally, we had said that I was looking for the value for b, but as it turns out, there's 2 possible values, because you could either have b being positive 2 or b being negative 2, and in either case, you would have exactly the same period. So actually, there's going to be 2 answers to this question. You could say that this is 3 cosine of 2x, so it's a cosine function that's 3 times as big and half as wide as the original. Or you could say it's a 3 times cosine of -2x. That would also have the same amplitude of 3. It would also start at +3 and start heading down and then back up. And the -2x, that would mean that we'd have a stretch and also a flip horizontally. But of course, since our graph is symmetric around the y-axis, it could be flipped or not, and it would look exactly the same. So as it turns out, we've got 2 different answers to this already, which is you could describe it as a cosine graph that's been stretched and stretched again horizontally, or you could describe it as a cosine graph that's been stretched vertically, then stretched and flipped horizontally. If we wanted to, and I'm going to skip this for now, but if we wanted to, we could also describe this as a cosine, instead of as a cosine graph, we could describe it as a sine graph, because remember that a sine graph, if you shift it, that's what a cosine graph looks like. So I could imagine this as also being a shifted sine function. I just wanted to make my life easy on myself, so I'm not going to try to think about what kind of horizontal shift is going on that would make this a sine graph. I'm going with the easy way out and saying it looks more like a cosine graph, so we'll go with that for its definition. Now, when it comes to the graphing of our trig functions, there is a little bit of simplifying that we could do, and I think it's a nice idea to use what we already know about our trig functions to make our lives easier. So one of them is the business of these horizontal flips. If our number in front of the x turns out to be something negative, we always have a workaround, and that's because our functions, we know that cosine is even, we know that sine is odd, and so we can use that to our advantage. So if you were looking at y equals 5 cosine of -3x, my claim is you could just graph 5 cosine positive 3x and you'll get the same graph, and the reason for that is because cosine is even. And because cosine is even, that means cosine of some negative angle is the same thing as cosine of the positive version for that angle. Or in other words, cosine is just sort of absorbing that negative. So when we look at 5 cosine of -3x, that is the same thing as cosine of positive 3x. Similarly, you could do something with this. If I had negative 2 sine of negative 4x, I could say that that's apparently the same thing as positive 2 sine of positive 4x. And the reason for that is because I know that sine is odd. And because sine is odd, we know that that means that if you had a negative number in front of the angle, that negative could come out in front. So in other words, if you had negative 2 sine of negative 4x, the odd property of sine says, well, you could take that negative out in front, and you'd have negative of negative 2, which is positive 2, times sine of positive 4x. And that makes my life a little bit easier because now if I'm thinking horizontally, I just have to worry about stretching. I'll never need to worry about flipping because I can always just use the symmetry to take care of that for me. So now what we're going to do is do a little bit of graphing, and we're going to graph our stretched cosine or sine graph. And basically what we're going to do is be a little bit more efficient than we've been in the past. So up till now, when we've been graphing functions with transformations, we've been doing our transformations one at a time. So that meant if we had a horizontal stretch and a vertical stretch, we would do them separately. But of course, these two things could be done at the same time because a horizontal stretch only affects the x values and a vertical stretch only affects the y values. So I really could do both stretches simultaneously. So my plan here is if you had your function a sine bx or a cosine bx, then start off with your basic 5 points, the ones that we looked at the very beginning of this section. Once you've done that, then just transform the x and the y coordinates. Multiply every y value by a, divide every x value by b, and then once you've got that, you have your transformed 5 basic points. Plot them, and away you go. Connect the dots, and you've got one full cycle. And then you can just use periodicity to figure out the other cycles. So 2 little fun facts that are good to know. So of course, the period for our trig function, sine or cosine, is going to be 2 pi divided by absolute value of b. And when we're thinking about how far are those tick marks from each other, if we're going back to our graph, remember that the tick marks there's 5 of them in total, but they really are splitting up our period into 4 equal-sized chunks, and that's the reason why the distance between the tick marks is exactly 1/4 of that full period. So for the example that we just looked at, that graph had a period of pi, so how far are the tick marks from each other? 1/4 of that, which is pi over 4. So every pi over 4 units, that's where the next tick mark is. So the next tick mark after pi should be pi plus a pi over 4, which is 5 pi over 4. And you can figure out all the next tick mark values as you go down just by adding pi over 4s, or by subtracting pi over 4s if we're looking for tick marks off to the left. So I've got all the ideas ahead of me to work with. I'm basically going to start with my 5 basic points, transform those 5 basic points, plot them, connect the dots, and then life is good. So my plan here, I want to sketch 2 cycles of y equals 2 sine of negative 5x. And of course, first thing I'm going to do, I'm going to use that odd property that we had for sine. Sine is odd, which means that negative can come out in front. So I could really say that it's negative 2 sine of 5x. And so now I'm going to start off with my basic 5 points. And for sine, or for cosine, the x values that we start with are 0, pi over 2, pi, 3 pi over 2, and 2 pi. And then for our y values, for the y values for sine of x, it starts at 0, up to 1, down to 0, down to -1, then back to 0. So those are the same 5 points that we had at the very beginning of this video. Now for the transformed graph, all I need to do is a couple of things. I need to, number 1, take all of my y values, and I'm going to multiply them all by -2. I'm going to take all of my x values and divide them all by 5. So to graph negative 2 sine of 5x, I'll take all of my y values and multiply these all by negative 2. So 0 times negative 2 is 0. 1 times negative 2 is negative 2. 0 times negative 2 is 0. Negative 1 times negative 2 is 2. And then 0 times negative 2 is 0. For all of my x coordinates, I'm going to, like I said, divide them all by 5. But of course, if we're taking x values and dividing them by 5, that's the same thing as taking x values and multiplying them by 1/5. So that's probably going to be easier for me to think about. 0 times a fifth is 0. Pi over 2 times a fifth would be pi over 10. Pi times 1/5 is pi over 5. 3 pi over 2 times 1/5 would be 3 pi over 10. And then finally, 2 pi times a fifth is 2 pi over 5. So there we go. We did our work to figure out what our 5 basic points are. And now all I'm going to do is start plotting those 5 points so I can graph my one cycle, and then I'll do my second cycle after that. So I've already kind of cheated here, getting my axis created in advance, but if you were drawing by hand, then you would start off by putting your 0, pi over 10, pi over 5, 3 pi over 10, 2 pi over 5 on the x-axis. And of course, if you've got tick marks at positive pi over 10 and so on, then you'd also have negative of all of those on the negative side. And now I'm just going to start plotting my points. So I'm going to plot my points. We had 0, 0. We had pi over 10, negative 2. Pi over 5, 0. 3 pi over 10, 2. And then 2 pi over 5, 0. And that's one full cycle. And I'm going to do my best to make this look nice. And there we go. Just as a little drawing tip, you might have noticed I did this in sort of 2 pieces, and I think it's probably easier than trying to draw it as one smooth curve in one go. At least it is for me. So I always sort of draw it as a parabola opening up shape, then a little parabola opening down shape. It's not exactly a parabola, but roughly that kind of a shape. And that is a little bit easier for me to do in sort of 2 pieces than to try to get it all nicely connected in one. Of course, I'm going to need to do a little bit of labeling, so I have to label any of these points that are not at a tick mark on the axis. So that's the pi over 10 negative 2 and 3 pi over 10 positive 2. And then now to complete my second cycle, basically I'm just going to do the same thing over here. So my next round of points, if we're sort of going backwards and imagining what happens next, we should be going up, then back to 0, then back down, then back to 0. So my second cycle will look similar to the first. Okay, not bad. And now just a little bit of labeling, and we are finished. So negative 3 pi over 10, negative 2. I've got negative pi over 10, positive 2. And then the last thing, of course, that I want to do is label my graph. And when I do that, I'm going to label it with the original equation. So what we've graphed here, negative 2 sine of 5x, is the same thing as our original function, 2 sine of negative 5x. And I'm going to label it with that original function, 2 sine of negative 5x. There we go. That's our sine graph. It's been stretched vertically by a factor of 2. It's been compressed horizontally, and there we go. 2 cycles, and we're finished. Let's do another one. So here we've got a cosine graph, and again, I'm going to do a little bit of cleaning things up first. First thing that I'll probably do just to make my life easier is, as I did before with this x over 2 business, rewrite it as negative 1/2 x. And then the second thing I'm going to do is say that, well, I know that cosine is even, so that negative inside the negative half is really going to be absorbed. I can just say that it's y equals negative 3 cosine of positive 1/2 x. So that means I have one less thing to think about. There's no horizontal flip really to worry about. I'll start with my basic shape. And my 5x values, 0, pi over 2, pi, 3 pi over 2, and 2 pi. And for my graph, y equals cosine of x, the basic 5y values are starting at 1, then down to 0, then to -1, then to 0, then to 1. So we're always starting with the basic 5 points, the ones that we started with at the start of this section, and then we'll just transform them. And again, the transformations here are one of them vertical, one of them horizontal. I'm going to just get myself going here. So we are going to find the y values for -3 cosine of 1/2 x. And for the x values, I'm going to take every x value and divide by 1/2. And of course, if we're taking x values and dividing by 1/2, that's the same thing as taking our x values and multiplying them by 2. So for my new x values, I'll take the old ones and multiply them all by 2. 0 times 2 is 0. Pi over 2 times 2 is just pi. Pi times 2 is 2 pi. 3 pi over 2 times 2, the 2's will cancel, leaving 3 pi. And then 2 pi times 2, that'll give me 4 pi. For the y values, I'm going to take all of the y values I originally had and multiply them all by -3. So I have -3, then 0, then 3, then 0, then -3. And now that I've got my 5 basic points, we're ready to go. So we can see that our tick marks are going to be going up by pi each time. So when I set up my x-axis, I'll set it up so that I'm going up, like I said, by pi each time. And then for the y-axis, I need to go as big as 3 and as small as -3. So let's plot our first couple of points, and then away we go. So our y values, we had our points were 0, -3, then we had pi 0, then 2 pi 3, then 3 pi 0, and then 4 pi back to -3 again. So try that again. There we go. That's a little bit better. There we go. That's one full cycle of my cosine graph. And of course, if I wanted to draw a second cycle, I just need to repeat that pattern. So to 0, to 3, to back to 0, to back to -3. And then only thing left to do is a bunch of labeling. And that's the one, I guess, difficulty or less nice thing about graphing a sine function or a cosine function is there's guaranteed going to be points that you will have to label, and I do expect you, of course, to label all of them. Any one of those points that's not at a tick mark on the axis will need to be labeled. So here we wound up with 4 things in total where we needed to label them. And later on, when we start introducing vertical and horizontal shifts, we're going to see there'll be even more points. In some cases, all of the points that we plot will need to have a label on them. But for this one, we look like we're in good shape with the points that we've already plotted and labeled. So now I can just put this equation down, -3 cosine of -x over 2. And there we go. We've got ourselves a well-labeled, graphed, transformed cosine function.